Hello students, here we're looking at the chain rule, and now we're going to look at functions that are based on other functions that may or may not have things that we're comfortable in the way that they're written. That was a really awkward sentence, but that's okay. So we're looking at functions based on other functions and how to kind of deal with this in kind of a unique context. As usual, the Khan Academy stuff on your version should be there, and let's go. All right. So we're trying to find derivatives of these things. And the problem that we have here is that they're not based on the right variable. So we might think about this as like 5y being like 5f of x. And if I asked you to find the derivative of this, the best you could tell me would be this would be 5 times f prime of x. Because we don't know what that function is. So we deal with that with something called implicit differentiation. I'm just going to erase that to give us a little bit of room here. So if I've got z is equal to 5 times y, if we want to take the derivative of z and the derivative of 5y, we can think about this in a couple different ways. The first is that the derivative of some function z that may be related to x is going to be z prime basically of x. Normally, this would just be 1 because the derivative of like x is 1. But because we're taking this with respect to the wrong variable, we end up in that kind of weird situation. The second way of thinking about this is that we can think about the derivative of z with respect to x, we know can be rewritten as dz dx. That means the same thing as z prime. That means the same thing as any of the other derivative forms that we have, and can be kind of useful here. In terms of the other side of this, we talked about that a little bit. We said that this would be 5 times this derivative of y, whatever that is. We don't know what that function is, so we can write that as y prime. At this point, we're done. We can't really go any further than this because we don't have anything else to do. By the way, using the notation in terms of dy dx notation, this would be 5 dy dx. Please be aware these are not actually fractions. I can't just cancel out the dx on both sides. We do some things that are not mathematically okay in calculus. This is not one of the places that you want to be doing things like that. Okay, so let's look at the other side of this. I'm going to do the derivative of w is going to be dw dt, otherwise known as w prime. And then we've got the derivative of cosine of y squared. All right, we've got a chain rule thing going on here, so this is going to be the derivative of cosine is negative sine of y squared. And then we've got to do the derivative of the inside. So the derivative of y squared, and I'm going to think about this as like f of x, the whole thing squared, would be 2 times y to the first. And then we have to do another chain rule. We have to multiply this by the derivative of whatever is on the inside here. And the derivative of y with respect to x, I don't know why I did t there, is going to be dy dx. All right. There's also kind of a shortcut way to think about this, which is this. If you're taking the derivative of something using a different variable than it's written as, for example, the derivative, now I will use t, of 3x squared. Because we're using a different variable, we take the derivative as normal, so that'd be 6x. And then we have to multiply it by the derivative of that variable, so in this case, dx dt. We could rewrite that as 6x x prime, and that would be okay as well. The shortcut here is just that every time we use that different letter, we need to include that prime as well. All right, so we've got some crazy curve going on here, And we're trying to find equations for horizontal and vertical tangent lines. I don't really want to go there without calculus. So let's talk about this in terms of calculus. Vertical tangent lines happen when the derivative is undefined, so dy dx is undefined. And horizontal happen when dy dx is equal to 0. In either case, we need to find some derivatives here. And I don't know, I guess I'll start taking the derivative with respect to x because I know how to deal with those as slopes. So looking at this one, if I take the derivative of x minus 4, I made that parentheses too big on the left side, x minus 4 squared over 9, plus the derivative of y plus 3 squared over 4 is equal to the derivative of 16, all with respect to x. All right, derivative of the first part is going to be 1/9 times 2 x minus 4 to the first, and the derivative of x minus 4 is 1, so we're okay there. For the second part, we're going to have 1/4, I'm just moving the fractions out in front, times 2 y plus 3 to the first, and then we have to include the derivative of y here, dy dx. And the derivative of 16 is going to be 0. Okay. This is kind of a mess. We're trying to find a slope. In other words, we're trying to find dy dx, which we also know as y prime. So this is what I'm trying to solve for. I might move the x stuff to the other side, and we end up getting 1/4 times 2 is a half, y plus 3, dy dx, and on the other side we're going to have negative 2/9. I'm just going to put that x up top to get dy dx by itself. We know we need to divide by that y plus 3, so that's going to end up as a y plus 3 on the bottom. And I know I've got to multiply by 2 to get rid of a half, and that's going to give us negative 4 on top. All right, so let's take a look at this answer and talk about what this means. We've got an expression for slope that's based not only on x, but also on y. And if I take a look at my graph, if I wanted to find the slope at any point on here, what this is saying is that we need to consider both the x and the y value. Part of that is because if I wanted just the x value, there are two different slopes that we could get. In dealing with this, and by the way, this is a way more complicated situation than what we're going to have to really work with. But in dealing with this, we have to use both x and y in order to make some sense of that. Okay, so let's take this one step further. So we've got dy dx, the slope, is equal to negative 4/9. Then we've got x minus 4 on top, y plus 3 in the bottom. Does it make sense that for a slope to be 0, we're looking for the place when the numerator is equal to 0? Because if we've got 0 divided by stuff, that answer is going to be 0. So for dy dx is equal to 0. In other words, the slope equals 0. In other words, y prime equals 0. We're really looking at negative 4 times the quantity x minus 4. In other words, when x equals 4. And visually, we can see that. We got 4. Those two things would definitely have values that part is equal to 0. I like it. All right, so what about the other condition? The other condition is when dy dx is undefined. We know that being undefined happens when we're dividing by 0. So one of the things we could consider is that if y plus 3 equals 0, that would cause us to divide by 0 in this function. So we're looking at when y is equal to negative 3. Y equals negative 3 happens here, and I can't really see because of, there we go. Oh no, I can do it. Okay, and that makes sense based on this picture. We could then plug these values into our equation, figure out the x and y values, and figure out that for the equations for these vertical and horizontal tangent lines. Much more commonly, we're going to be finding the derivative of expressions like this that involve multiple pieces. There are two things I need you to be really careful of here. The first is what we're learning new today, which is this implicit stuff, which the y prime stuff. The second is that between each of these pieces, we're multiplying things, so we have to use the product rule. I'm going to show us how to find the derivative based on x, and I'll leave you to find the derivative based on t on your own, which is the second piece of this. So I'm going to go piece by piece. The derivative of 3x squared y, in this case I'd have like f and g for 3x squared and for y, and we're looking at 6x times y plus 3x squared. The derivative of y is 1, y prime. All right, second set. So we got minus 5xy. I'm going to do the same thing. We've got f and g for my product rule. So we've got minus 5y and then minus 5x. The derivative of y is going to be y prime. So 1 times y prime. And then we've got the derivative of y squared is 2y. Because we're using the wrong variable to take the derivative, which is the x, I need my y prime as well. And finally, the derivative of 4 is going to be 0. All right. This ends up being kind of like a weird combine like terms problem. I've got to get my stuff with y prime on one side and my stuff with not y prime on the other side. So I've underlined my three things with y prime. I'm going to let those kind of stay where they are and move the other pieces to the other side. So I've got 5y, cool, and then I've got 6xy that I need to move, so minus 6xy. I like it. That leaves me with 3x squared y prime minus 5x y prime plus 2y y prime. All three of these have a y prime. I'm going to factor that out, leaving me with 3x squared minus 5x plus 2y. And that's equal to 5y minus 6xy. When we get y prime by itself, we're left with 5y minus 6xy divided by 3x squared minus 5x plus 2y. That's the end of this problem. We're trying to get the derivative of this function with, or not this function, this relation with respect to x. In other words, trying to find dy dx, which is the same thing as saying y prime. We took the derivative. We were careful with a couple of different product rules. And any time that we took a derivative of something that involved a y, we added a y prime afterwards. We then gathered the stuff with y primes on one side. That's what's happening here. We gathered the stuff on the other side that did not have a y prime, and we factored out a y prime so that we could divide to get y prime by itself.